We're going to spend a few minutes today collecting data for an experiment which relates to what we've done over the last several days in class, just an application of Newton's second law. We've done over the last couple of days a few what we call pulley problems, where maybe you got a table, a pulley, and you got an object on the table like this, and then you got an object hanging off the edge of the table like this. You can see in the picture that I have inserted in this presentation here, you can see that I've got essentially that set up right now. You can see a dynamics track right here. You can see a pulley on the end of it. You can see a dynamics cart right here on the track. Okay, and there's a string. I don't know if you can see that or not, but there's a string that's connected from this cart going around this pulley. Now, there should be a mass on the end of that string as well. In the picture, I've got the mass right there. Obviously, when I actually set this experiment up to do it, the mass is going to be hanging off the end of it. We're going to perform an experiment where we're going to essentially let this go. We're going to measure its position and time, and then from that, I will get for you a velocity time graph, and then from that velocity time graph, you will get, yourself, the acceleration. Okay, how are we going to get that position and time? Well, same as we had before, we're going to use our AirLink apparatus. You can see the motion sensor right here on the end of this dynamics track, and then you can see this AirLink transmitter that transmits the position time data to my iPhone. Okay, I will take that data, I will plot the graph for you, the velocity time graph for you, and then I will post that graph on my website where you can literally just download the graph. Okay, make sense? There are a couple of things that we need to measure before we get going on this. The two main things that we need to measure before we get going are the two masses, M1 and M2. M1, you don't need to copy any of this down right now, okay? Unless you want to make a couple little notes, but in the end, I'll even give you this template, okay? M1 is going to be the hanging mass. So we've got to measure the value of the hanging mass. M2, this should be labeled over here actually. M2 is the mass of this cart. I've already measured the mass of this cart, and it was 498 grams. So M2, we're going to say is 498 grams, which we're going to convert to kilograms and make it 0.498 kilograms. M1, the mass of the hanging mass, in the first trial that we're going to do is 100 grams. So we're going to make that 0.100 kilograms. That's all the data that we've collected so far. Next comes the actual experiment where we're going to find the position time data and ultimately get a graph from that. So let's set that up right now. Okay, I've got the iPhone synced to it, so the Bluetooth connection is there. I'm going to bring back the cart. I'm going to get a volunteer up here if I can to hook the mass onto the end of the string on the other end so that we have something that's hanging. Mass 1 that's hanging down here. Should be a little loop there, Fraser. If you want to hook it on, thank you. And then just thread it over top of the pulley there. Pull that pulley up. We'll thread it over the top of the pulley there. Yeah, that's good. That's good. Okay, I'm going to create the experiment on my iPhone right now. Call it experiment number 1. Okay, Fraser, I'll just get you to stay up here, okay? Let's get you to stay right here, because I'm going to need you again in a moment here. Experiment number 1, I'm measuring position. Now my sample rate, the default sample rate on this is 10 hertz, and you guys probably don't remember that from the last time you guys used it, but you can change the sample rate. I'm going to change it to 50 hertz. So instead of getting 10 clicks per second, instead of getting 10 measurements of position per second, I'm going to get 50 of them. The reason I want to do this is because this experiment, this trial is going to go very, very quickly. And if I go 10 per second, I'm not going to get all that much data. If I go 50 per second, then I'm going to get a lot more data, 5 times the data, which is going to give you a nicer graph. Okay? So I'm holding this cart. Okay, I've got the motion sensor set up here. Okay, I'm ready to go. I'll click on the experiment here. And I'm going to click on the little green button if you remember this. Okay, we'll review this on Friday as well because you're going to do an activity with this on Friday yourselves, just a different activity. Press the little green button, and I'm going to let this cart go. Oops, should ask Fraser, I guess, to stop the cart before it went off the end. Okay, I've got some pretty good data, it looks like, on my iPhone right now. This is position time graph that it plots itself. So of course the position time graph should look like this. And you can see that it does, right? It curves upwards if you look at the phone here right now. I'm going to take that and I'm going to convert that to a velocity time graph for you. And I'll post the velocity time graph online so that you can download that and just insert it into your document, okay? Now we're going to do one more trial, but this second trial is going to involve a different M1. Instead of 0.1 kilograms, we'll take a different mass. This time we're going to take a 50-gram mass, so instead of being M1, 0.1 kilograms, M1 is going to be 0.050 kilograms. You probably should write down those numbers, actually. Trial 1, M1 was 0.1 kilograms. M2 was 0.498 kilograms. In trial 2, M1 was 0.05 kilograms, and M2 is still the same value. That's 0.498 kilograms. Write those numbers down because those won't be available for you online, okay? And if you don't have those numbers, you're not going to be able to complete this experiment. So we've got this, the first mass, 0.05 kilograms, hooked up to that now. Rutger, thank you. Okay, we're gonna fix this again. We're going to pull this back. Rutger, can you hook that on there, please? I'm going to create a new experiment here. I'm going to change the sample rate again to 50 hertz. I don't know if you guys noticed, but when I was doing that, that motion sensor was clicking way, way faster than it was when you guys did your experiment with position time earlier this year. Clicking way, way faster because it's taking 50 measurements per second instead of 10 measurements per second. And again, the whole point of that is so that we get a lot more data. It happens very, very quickly. If it happens in, say, a half a second, this way we get 25 data points instead of 5 data points, which gives us a lot better graph, obviously. All right, so I go to this new experiment. It's all set up, ready to go. Would you expect this one with a mass of 0.05 kilograms hanging off the end of it? Would you expect it to accelerate at a greater rate or a smaller rate? Accelerate faster or slower? We got half the mass hooked up here, half the mass hanging over the edge. Hayden, it should go slower. In fact, we would predict probably an acceleration of half the rate. Would that make sense? Okay, we'll see when we actually go to analyze this data if we get half the rate or if we're overlooking something when we're making that assumption here. All right, so ready to press the green button here on the iPhone. Okay, ready to let this go. Rutger, can you stand at the end there and catch this so it doesn't go off the edge like you did last time? Hey, ready, set, go. Thank you. So this time we get a curved line again. It's a little bit probably hard for you guys to see the curved line from where you are because it's straighter than the last one was. Trial 2, it looked more like this. It still curved upwards, but it didn't curve upwards as quickly as it did the first time. Why not? Can you see the curve in that? Yes, did you see? Yes. Why doesn't it curve up as quickly as it did in the first one? Hayden knows the answer to this because he answered my last question. Hayden? Yeah, if it's a lower rate of acceleration, the line isn't going to curve upwards as quickly. Does that make sense? Okay, so I will transfer that data to myself, and then at some point later today, I will get that data converted to velocity time, and then I'll get a velocity time graph plotted, and I'll post it online. Okay. By about 5 o'clock tonight, you guys should be able to find on my website, look under Physics 20, you guys should be able to find the data for that. And if you have any trouble finding the data for that, then make sure you just send me an email, and I'll send you a link to it, so that you can just click right on the link in your email. Got it? All right. So what are we going to have to do with that now? Well, you're going to find this template that you see up on the board here right now online. I'll show you in a few minutes where to get that. Let's assume right now that you know where to get that. Okay? Let's assume that you know where to get that and you've got it already, you've downloaded it already. Let's assume that you've also downloaded the velocity time graph, which should be, by the way, which shape? What should the shape of the velocity time graph be? Right? The position time graph was curved upwards. The velocity time graph should be what? Curve upwards? No. Should be a straight line. The velocity time graph should be a straight line. Can you tell me why it's a straight line? It's constant acceleration, right? It's not a 9.1 acceleration. It's something lower than 9.81, but it's still going to be a straight line because it's still a constant rate of acceleration. Now, what you're going to have to do with this twice, because you're going to have two graphs, one for each trial, is find the rate of acceleration. And we're going to do that by drawing a line of best fit. You have to draw that line of best fit, okay? Find the slope of that graph. Pick 2 points on that line of best fit. Okay, pick 2 points on that line of best fit, and then go acceleration is equal to delta v over delta t, or you can say slope is equal to delta y over delta x. It doesn't really matter because they both end up being the same thing. Vf minus vi over tf minus ti, or y2 minus y1 over x2 minus x1. Get a value for the acceleration. Let's say it's 3.4 meters per second squared, whatever it works out to be. Okay, whatever that value of acceleration works out to be, you're going to record right here on the template that I give you. But I also want you to show the work for that. Okay, in other words, show A is equal to delta V over delta T, or slope is equal to delta Y over delta X. Show your 2 points on that graph, okay? Show the numbers that you're plugging into that equation. Get a number for that, okay? Write that number down. If it's 3.4 meters per second squared, then that's what it is. Okay? Once you've got that slope, record it down here as well. 3.4 or whatever it works out to be. Then comes time for the analysis. Right, Wayne? Then the analysis. The analysis down here involves adding m1 and m2 together, multiplying it by the acceleration. So it would be 0.05 plus 0.498 multiplied by 3.4 meters per second squared. That gives us the net force. Okay? Net force is m times a. Total mass times acceleration. Okay? So it's this mass plus this mass times the acceleration. When we were doing these problems over the last couple of days, we said F net is equal to the sum of the forces. F net was m times a, and that mass was the total mass, m1 plus m2. So figure that number out. Put it in right there. The second column of that table is m1 times g. In other words, it's the force of gravity acting down on the first mass. Get that number. Okay, write it down. And then you've got to answer one more question. Does Newton's second law hold in this experiment justify your answer? Newton's second law says F is equal to m times a. If m1 plus m2 times the acceleration, that's m times a. If that equals the force that's applied here, which is really what supplies the net force, and that's going to be m1 times g. If those two are equal, then Newton's second law must hold. The net force is equal to the sum of the forces. If those two don't equal each other, then Newton's second law doesn't hold. Does that make sense? You're going to do this twice, right? For trial number 1, where the mass of object number 1 was 0.1 kilograms, and for trial number 2, where the mass of object 1 was 0.05 kilograms. It's a really quick thing to do. It's a really quick assignment. You're going to do this, you're going to write this up, and you're going to hand it in to me on Friday. Okay, there's no reason whatsoever why we shouldn't have it all ready to go on Friday, because it's so quick and it's so easy. I've collected the data for you. I'm even going to give you that velocity time graph. All you have to do is do a couple calculations. Okay? Now, I said earlier we were going to do this a little bit differently in terms of submitting it, in terms of format and so on. I'm giving you the template. I'm giving you a graph. What I'd like you to do, what I'd like everybody to do, first of all, pay attention to what I'm going to do here, and then follow these instructions as to how to submit this, okay? You're going to go to google.com or google.ca or whatever it is. You're going to have the option of signing in. Every single one of you right now, I'm not sure if you realize this or not, but every single one of you right now has a school email address, and every single one of you has a Google account through the school. Your email is processed through Google now. It never used to be last year, but it is this year. And that's good news because it also gives you access to a whole bunch of other Google features, including something called Google Drive, which is a fantastic feature. Okay, that allows you to save everything you do in a cloud on Google Drive. Then when you want to access it somewhere, including on your iPhone or the computer in the library or your home computer, all you have to do is go on Google, log in, and get it. You never have to worry about carrying around a jump drive or emailing something to yourself or any of that. It's all there. What it also does is allows you to share something with me. So for instance, if you write up a lab, you don't actually have to print anything or email anything. All you have to do is click on a setting which allows you to share it with me. That allows me to see it, it allows me to mark it, and it allows me to comment on it, and nobody ever has to touch a piece of paper. It also allows me to give you a template to fill in. Okay? What I've done yesterday is prepared the template that I showed you in the slideshow a minute ago, and I've shared it with you. I've shared it with everybody. Here's how you're going to access it. Okay, you're going to sign in to Google. Okay? I'm going to sign in not in my school account. I'm going to sign in another account because I've put this document in my school account. Okay, I want to show you what it's going to look like for you, not what it looks like for me, the person that has already shared it. Okay, so I'm going to sign in this other account that I have, which is HTA Dickie. For you guys, it will be your first name, your last name, and then redeemer.ab.ca, whatever your email address is. You sign in with your Redeemer email address. Okay? Your password is your Redeemer email password. If you don't know what that is, you can check at the library and find it out. Okay, you should see something like this when you've done that. Okay, it hasn't changed much, except in the top right-hand corner, it's got some information that's customized to you. Okay, we're going to click on Google Drive here. And that's going to take me to this folder that has all of this stuff. Okay, going to take me to this folder that has all of this stuff that I've prepared. Most of this stuff isn't going to be relevant to you guys whatsoever. It's just documents that I have stored on there, some of them that I share with other people, some of them that I just store there as a backup so that I can access it from anywhere. Literally, guys, this is how useful this is. Hey, last week I went to cross-country provincials with the cross-country team. We had a roster and we had a information booklet and so on. Okay, I'm accessing that information booklet on the computer a few days before that. I save a copy of that in my Google Drive. So what do I do when I need to access something literally at a meet, kind of, off in, where were we, Drayton Valley, Alberta? I just go on my iPhone, I click on Google Drive, and then I access that exact same document that I viewed on my computer the other day that I saved to my Google Drive. Okay, that's the real benefit of this. Now, there's a whole bunch of stuff on there. There's only one thing that you guys want. Okay? So you guys will have a link to this document. Okay, this template, which you have access to. You have the ability to edit, you have the ability to copy, you have the ability to add things and subtract things, whatever. Here's what I want you to do with it. The very first thing, when you're in your Google account, okay, the very first thing is go into File, and I want you to make a copy. Okay, I don't want you to change that. Okay, I want you to make a copy of it. Here's the name that I want you to give to it. I want everybody to name it Newton 2 activity, your name. So Joe Smith, or whatever the case may be. So I've just made a copy of it. It's called Newton 2 activity, Joe Smith. If you go back to my Google Drive folder, you should see a copy of that now in my Google Drive folder, my Newton 2 activity, Joe Smith. Okay, so that's now your copy of it. Okay, now you can go into that and you can edit it. It's just like it's Microsoft Word, except it's a word processor that's actually a part of this Google Drive. And the beauty of this, too, is that it saves everything automatically. You don't ever have to worry about losing data. The power goes off. Well, you've just lost the last 5 seconds of your typing. That's about it. Because it saves everything automatically. You never, ever have to click save once. Okay, if I type in one letter, within 2 seconds, that one letter is going to be saved there automatically. So you're going to go into here. You're going to type in your name, you're going to type in the date, the stuff that you always would. You're going to copy and paste the graph that I put online. You're going to copy and you're going to paste it into right here where it says analysis, right here. Okay. Then you're going to do your thing. You're going to calculate the value of the slope, showing your work. You're going to type in your data there. You're going to type in your analysis right here. It's the value of M1 plus M2 times A, the value of M1 times G. You're going to type in your little conclusion, which is, does Newton's second law hold? And then you're going to repeat that with the data for the second experiment. Does that make sense? Then, finally, once you've done all that, you're going to click on this button in the top right-hand corner where it says Share. Okay? You're going to share it with me. You're going to invite people. Well, you're going to invite person. You're going to invite bdickie@redeemer.ab.ca. I'm going to get an email as soon as you do that you're finished and that you've shared it. That will allow me to go online into my Google Drive account and look at your lab and mark your lab and comment on it and mark it there. Does that make sense? So we're kind of accomplishing 2 things today. We're kind of trying to do 2 things today. One is verify Newton's second law, and that's the main point of this. But I also want to experiment with this Google Drive thing and show you in the end, after you've kind of gotten the hang of it, how easy it is and how efficient we can make things down there. Did you guys just hear that little sound there? The sound that my iPhone just made? That was the email that I just got that told me that was shared, this new document was shared with me. Make sense? So we have until Friday to do this. Okay. What I'd like you to do, please, is work on this tonight. Okay. Share the go through this process tonight. Even if you don't get the whole thing written up, if you just get into Google Drive and figure that whole thing out tonight so that you can ask me questions on it tomorrow. Share the document with me. Okay. Share the document with me, but only do that when you're finished. Does that make sense? Unless, that is, you want to share it with me to ask me a couple questions. You want to share it with me and say, look, I'm getting some numbers here that don't really make sense. Can you help me with this? Okay, then you can share it with me and I can take a look at it that way. Otherwise, just wait till you're finished before you share it with me. All right? Question? Can you use your personal email account to access it? You could. Yeah, you could. Yeah. I'll post a link to this, to the original file on my website. I'll post it. You'll see where it is, where the link is, and that will allow you to access the link. All you have to do at that point is literally copy and paste the link into a browser, and then it's going to ask you to log in with a Gmail account, and you can either log in with a personal Gmail account or your school Gmail account. I would recommend the school Gmail account. Everything's set up well to kind of function really well between you and I with that. But at the end, I think it should work really regularly. Okay. How many people have used their school email this year? Nobody. One person. How many people have used this Google Drive before? Just 1 or 2. Okay. I'm telling you, this is a very, very positive thing for us. Okay, not just for physics, but for all kinds of things as you go through school the next 2 years. For collaboration, I mean, you can share a document with me. I can comment on it. Okay, you can share documents with each other. You can even, in fact, if you're given a group project, you can actually even work real time together from separate locations on the same document. Okay, there's a lot of things you can do with this. And once you start playing with it tonight, when you're working on this, and you're going to start seeing some of these things, some of these new